Kevin Arts. Today we're going to talk about how to measure association between two random variables. So let's say that we have two sets of random variables, x1 through xn and y1 through yn. And we're interested in knowing how these two are related. Are they associated? Are they inversely associated? Are they directly associated? Are they not associated at all? A few aspects of the measure we might want to use to measure the association of these two variables are listed in steps 1, 2, and 3. So one reasonable condition is that we like something that's positive if xi and yi are directly associated, and negative if they're inversely associated.
What do you mean by directly and indirectly?
Okay, so by directly, let's take the example listed here of height and weight. A direct association would be that if the height is higher, then weight is higher, and if height is lower, then weight is lower. Makes sense? Now, an inverse association would be the opposite of that. As height is lower, weight is higher. So, which doesn't make sense, but that's an example of an inverse association. So one aspect of the measure we would like to use to measure association of two sets of random variables is that its sign, plus whether it's plus or minus, reflects whether the association is positive or negative or inverse. Plus 1, so I'll write here plus 1 reflects association. Plus or minus association. Now another useful aspect of a measure of association between two sets of random variables is that it's scale free. In other words, 0.5 always means more or less the same thing. We'd like it to be bounded on -1, 1. That way, it wouldn't make much sense if the association was, say, 5 for one set of random variables and 10 for another, and we had no way of comparing those two things. So we'd like it to be bounded on -1 and 1.
Is that related to probability, which is bounded between 0 and 1? Is that the same idea, or it's a different idea?
It's a different idea, and it's different because we could bound it on anything. It doesn't have to be a -1 and 1. I could say that I want to plot it on -100 to 100 if I chose to interpret things that way. But at the extremes, what I'd like is that the relationship is perfect. So whatever I choose, whether it's 1 or 100 as my extreme value, that would mean that if my weight is, that means that height is directly, how height is perfectly related to weight. In other words, there's no other confounding factor. Do you understand what I mean by perfect association?
It's like they're equal, right?
For instance, that would be one example of perfect association, yes.
You mean they can be perfectly associated without being equal?
That's right. Let's say that height is twice weight. Or, I take that back. Well, weight is twice height, let's say. That would be another example of perfect association.
So I could take x squared.
X squared?
Yeah, like I say y is equal to x squared.
Well, under the type of association we're going to talk about today is going to measure linear associations. That's what correlation does. But you could potentially come up with something that would measure x squared. In fact, I think you talked about it earlier. So what we'd like is that it's bounded. So we'll say it's bounded, but it doesn't have to be -1, 1. But -1, 1 is a pretty convenient set of area to bound it on. And finally, because of this plus or minus reflects the association, what we'd like is that if the value of our association measure is 0, then that means that there's no discernible relationship between the two sets of random variables.
But you just mentioned you're doing linear relationship, so you mean no linear relationship? Or does that mean you can have any relationship if it's a 0?
Well, sorry, did you have a question?
No.
Okay. Well, it's true that there can be other forms of relationships. And sometimes other relationships can still look linear. We'll see a couple examples of that. So, your question was, can there be another form of a relationship?
If it's a zero.
If it's zero. There possibly could be, yes, actually. Well, it depends. Again, we could construct a measure that would capture a different type of a relationship, but the type that we'll talk about today will end up being zero when it's a linear relationship, or for certain nonlinear relationships. Now, sometimes a nonlinear relationship still has a linear component, and I guess just to give you, we'll do a quick diversion here. Let's say x squared, the example Roy had, and then it dots, according to that relationship, might look something like this. Now, certainly this is not a linear relationship, but it still has a linear component. You can see that it's roughly going up. Y goes up as x goes up. So you can see that many sorts of relationships still have linear components. Does that get at your question? Okay, that's good. All right, so we let it zero when no association. Okay, now let's introduce the first candidate, something called covariance. Okay, and we'll see whether it has these properties. Okay, I've listed the formula for covariance down in the next section. So let's kind of look at it and try to gain some intuition just from looking at the mathematical formula. Don't worry about the factor of 1 over n minus 1. That has to do with the mean being unknown, but we're not going to discuss that issue here today. Just focus on the formula and what it means for the xi and yi that we have this formula for covariance. Now, I've listed a few observations down below. And the first of them is that, well, covariance is positive if both of the values in that sum are positive or both of them are negative. Now, if both of them are positive, that means that when xi is above its mean and yi is above its mean, then we get a positive contribution to the sum. Now, by the same token, if xi is less than its mean and yi is less than its mean, a negative thing times a negative thing is, we learned the positive thing, and that will also give a positive contribution to the sum. So this formula, this sample covariance, has the desired property that covariance is positive when there's a direct association. Does everyone follow me there? Okay. Okay. Now, by the same token, it has a desirable property that when we have an inverse association, meaning that when xi is below its mean, yi is above its mean, then we have a negative thing times a positive thing in the sum, and that results in a negative contribution to covariance. So it has the desired property that plus or minus reflects association. Okay? Now let's look at the case of no relationship. Now in the case of no relationship, it's listed in point C here, xi is sometimes high and sometimes low when yi is low, and it's sometimes high and sometimes low when yi is high. So sometimes the contributions to the sum will be positive, sometimes they'll be negative, and we would hope that at the end of the day they cancel out and we get about 0 when there was no association. So in fact, covariance does have this desired property that when there's no association, it's valued 0.
But they're not going to be exactly 0, right?
That's true. That's true. It's not going to be exactly 0. But it'll certainly have lesser magnitude than when there's a true association. Would you agree with me there?
And is it true that the larger the n is, the more likely going to be 0?
The larger that n is, the more likely going to be 0.
If there's no relationship?
There's well, in fact, that does turn out to be true.
So is that related to the central limit theorem?
It is, yes. Wow, I can see you've been doing your homework. Hey, that's good. That's right. So far we've satisfied 2 properties of our desired association measure. Now let's look at the third. Now, if I have an xi that's really, really large, say 1 million, then the covariance will get really, really large because all it's measuring is these distances from the mean. So covariance is not bounded to any discernible thing. And that's why if you guys have a pen handy, you can fill in the blank with the big letters NO, because covariance is not bounded to -1, 1, okay? All right. Okay, so we have covariance and it's almost what we want for association, but not quite, okay? And that's where we introduce correlation, all right? It turns out that if we take this quantity covariance, and as you can see in the next section here, we divide it by the product of the standard deviations. Well, because the standard deviation is sort of a spread measure, this quantity ends up being bounded to -1, 1. And additionally, because all we did was divide it by something, it maintained the same properties of covariance in terms of plus or minus reflecting association, and 0 reflecting no association. But now, because we've divided it by these standard deviations, we've bounded it to -1 and 1. Now you may be wondering, well, why is this quantity bounded to -1 and 1? To see that, let's check the case of, you can check the case of perfect association, and I'll let you do that on your own. But I've listed in there a quick guide on how you would do it. It turns out that the covariance of x, and let's assume that y is equal to x, that would be the case of perfect association. And covariance of x and x is just the variance of x. And the variance of x is the standard deviation of x times the standard deviation of x. And in the denominator, we also have the standard deviation of x times the standard deviation of x. And then the quantity will just turn out to be 1. So it turns out that correlation is bounded to -1 and 1.
Wait. That seems to me a circular argument, is it? Because you just show, say, if they have perfect relationship, it's 1.
Right.
But if they don't have perfect relationship, how do we know it's less than the 1?
How do we know if it's less than 1 if there's
We haven't proved that, right? You're assuming this thing measures somehow monotonely, so if you prove... Right? I mean, is this that we have tried for every possible cases, or is there some better proof of this in between?
Yes, I'm sure there's a better proof. I don't have it off the top of my head here. But maybe to sort of get at the intuition, if you look at the individual components of the sum in the covariance, the highest we can make. You know what? I don't know enough to go on to answer your question perfectly, but you're right. There probably will be a better proof. For now, suffice it to say that yes, for non-perfect association, it will end up between -1 and 1. Okay. All right. Now let's discuss some intuition about correlation. Okay. We've gone.
Can I ask you one more question?
Sure.
You said at the beginning, says it doesn't really matter how you scale. You can scale to any sum set.
That's right.
Right. So why do we divide by these complicated square root stuff? You know, why can't we just divide by some maximum values just to make this thing some reasonable range?
Well, again, you could do that, but it's convenient that the quantity is always bounded to -1, 1. Because if we have, say, another set of x1s and y1s, and we want to compare their association with the association of these x1s and y1s, if you did what you just described, they wouldn't necessarily be comparable, would they?
Really? Because I can, for each one I got the covariance, which you easily calculate. I can divide by some numbers. For each data set, I divide some numbers to make them between 1 and -1. Would that be comparable to professor?
Well, no. Let's say that your second set of variables were on a different scale. In other words, they were all 10 times the first set.
I just divided by 10 times whatever the thing I divided before.
But that's what's happening in the standard deviation. If you picked exactly the number 10 to divide by, then that would be precisely what the standard deviation was doing anyway. Now, if you were to pick some other number, then there would be no guarantee that they'd be comparable. I think we'll have to, it's probably useful to look at a few examples to get some more intuition. So let's go to the next page. And I thought we could just maybe go around and taking a look at this first plot here. But let's try to order the correlations of these different sets of dots. Now, the red dots, of course, are one set. Then we have the black dots, the green dots, and the blue dots. And I think it would be useful to try to order the correlation of these different sets of dots. Okay? So let's see, between